Hello, I'm Sungho. I'm the member of the Line game team and currently working on Line just development. Today, I'm going to talk about what QUIC is and introduce Stellite and how we apply Stellite to Line games. For mobile game developers, one of the most challenging tasks is providing a fast and reliable connection in the wireless network environment. So we all know how much game users hate loading failures and disconnect issue. There are various reasons for wireless network problem, such as long connection time, packet loss, or handoff failures. To overcome this problem, Google developed open source protocol called QUIC. QUIC is a TLS HTTP2 protocol over UDP stack. It is one of the Chromium projects developed by Google. The QUIC protocol can make zero RTT request and recovery lost packet using forward error correction. Forward error correction recover the lost packet using XOR operation. QUIC support connection migration. This means that even if a client changes the source network address, it keeps the existing connection using by connection ID. It also provides TLS level security and multiplexing without H or hard write blocking for TCP and HTTP. QUIC support HTTP header compression for HTTP2 spec. To provide the better wireless network connectivity, we decide to introduce the QUIC protocol to our Line game and launch a project called Stellite. Stellite project is a client library and server application for QUIC protocol that aim to provide fast and stable wireless network. Since our project is based on the Chromium code, Google Chromium project, we took the project, the name Stellite, from Stellite alloy, which is one of the Chromium metal alloy. Stellite consists of Stellite QUIC server and Stellite client library. The client was developed to use with the Cocos 2DX and Unity game engine. It currently supports Android, iOS. Stellite QUIC server is an extension version of the Chromium's QUIC simple server. Now let's take a look at each part, client and server, more closely. First, I'm going to explain about the client development. When we developed the client part, we wanted to make it easy to use. In other words, easy to build and easy to apply and easy to switch to UDP, to TCP or TCP and UDP. And it should be available as a library type. And most importantly, it should support zero RTT request over QUIC protocol. The left one is the original network programming model used in the past. When we first launched the Stellite project, the initial plan was changing the model from left to right. But there was one problem. We had to consider how to switch back to C URL library. If QUIC would become unaware of any problem. So we turned to Chromium to see if they have any workaround for this matter. We found out that the Chromium browser solved the problem by using a QUIC discovery. QUIC discovery is a application layer protocol negotiation. It can switch the protocol from TCP to QUIC seamlessly. In addition, when QUIC is have any problem, it can switch to the TCP. We decide to use a combination of the QUIC and QUIC discovery in the Stellite client library. As a result, the client programming model Stellite become too similar to the Chromium's model. Today, we apply the QUIC discovery information, the Stellite. We brought the Chromium network session to library to Stellite. It made the Stellite support not only QUIC protocol, but PD, HTTP, HTTPS, and HTTP2 protocol as well. The first figure is the final output, the Stellite client library. You just need include the full header file and link a Stellite client library. Then Stellite is ready to use. To make the client easy to apply and develop, we try to minimize the dependency in several ways. First, as shown on the second figure, we remove the Chromium header dependency using port declaration and pimple pattern. Second, we made a shared library to minimize symbol conflict in OpenSSL STL library. OpenSSL library had a symbol conflict with boarding SSL, and STL library had a symbol conflict among the GNU STL and STL port and LLVM STL. We also include the thread model so that users don't have to make one by themselves. To compile a Stellite build for various platforms more easily, we use a Docker. Using Docker enables us to compile the Linux build on the Darwin platform and to build a QUIC server that run on the Linux environment. One time alone, we can build a platform such as Android and iOS, and Linux and iOS, yeah. Except Windows. Docker is also necessary to automate the multi-platform build process. Building is time-consuming without automation. So we wrote original build script using Python, used with Jenkins build machine. Our script uses Chromium build systems such as GYP, Gclient, and Ninja. We can specify the target platform and target output in the script. And the script will process the number of steps automatically from patching Chromium code and the tool chain to build. Okay. Now let's move on the Stellite QUIC server. Chromium provides a quick, simple server to help a developer try and test QUIC protocol. However, it is not fit for using the production environment. So we developed our own QUIC server extension. Key feature of the QUIC server extension are reverse proxy and multi-threading. In original game server structure, client access web server directly. In the new structure, to use a QUIC protocol, QUIC server has to be flexed between the client and web server. So we add a reverse proxy feature to our Stellite QUIC server. When our requests are processed on single thread, resources cannot be used efficiently. And throughput may be decreased as well. To prevent this, we adapt the multi-thread model to Stellite. In multi-thread model, main thread manages the worker thread and dispatch the UDP packet. And worker thread handle sending and receiving HTTP requests at backend. Next, I'm going to talk about how we test the performance of the Stellite QUIC server and what we did to improve it. We ran the series of tests to see how much throughput our server could handle and evaluate if there were any performance issues. These tests were done on a single QUIC server using a simple task model shown on the screen. Eureka is the name of the line game system used to run a server load test. The system uses a Docker and N-grinder in mainly test processing of HTTP requests. Using a Docker, the system creates a large volume of virtual client and run a task processing REST request. Since we have a plan to use with the HA proxy, we add the HA proxy also in the test model. Let's take a look what kind of the performance issues were discovered and how we solve them. Yeah. The first problem is the UDP socket overflow problem. Unlike TCP socket programming, UDP socket has to process both request and response in single socket. In other words, buffer size of UDP socket should be big enough to packet loss, avoid the packet loss. During the test, we discovered that the send buffer error rate as high as 100K. So we increased the buffer size, send and receive buffers, and solve the problem. The second problem was bottleneck in the single UDP socket dispatcher. On the multi-thread QUIC server, bottleneck occur when the main thread tries to process a task using own UDP packet, UDP packet and socket. Yeah. So we made the UDP socket in each worker thread and remove the bottleneck problem. The reason we could do so that worker thread had no dependency between them and reuse port option had become available since Linux kernel 3.8. The third problem is related to the second problem. The problem occurs after moving the QUIC dispatcher task to the worker thread. Processing first the QUIC package task and the reverse proxy task on the single worker thread. It caused the reverse response delay at the reverse proxy side. In consequence, we divide the QUIC dispatcher thread and the reverse proxy thread to reduce QUIC dispatcher preemptation cost and improve the response time. At the initial test, the TPS could not raise over 1005. After making the adjustment, the TPS were improved almost by 13 times. Likewise, at the initial test, the request error rate was far from ideal. It was as high as 1400. However, after adjustment, the error rate dropped to around 30. The error rate is within an acceptable range because connection can be converted to TCP through QUIC protocol using a QUIC discovery, allowing the service run normally. Stellite has a trial run with the line rangers and the line bubble 2. We test the Stellite client library using the speedy protocol and concluded that it was ready to roll out to the production environment. Stellite was the first foot into the operation with the line fighters, which was released in early September. And it is up and running smoothly ever since. We have a plan to integrate the Stellite QUIC server with the Line Game Cloud. This means that QUIC protocol will be applied to the entire Line Game platform. Also, Stellite QUIC server and HF proxy server will be able to work in pairs. The integration was already complete, and we are running tests at the moment. We have a last banner, our big announcement. We are open source Stellite today. So we would like to ask all of you and try and contribute to the Stellite project. Yeah, thank you for listening. Okay, it was done. If anyone have any question, please. Sure.
Thank you for the presentation. Do you have any plans to migrate from using Chromium to QUIC, which, per my understanding, is the semi-official version of the QUIC implementation cut out from Chromium by Google developers?
Sorry, I can heard about.
There's a library called QUIC, which is maintained by the Chromium developers. It is a library cut out from Chromium. Yeah. It's the protocol-only library. So do you have any plans to migrate from using Chromium to QUIC?
Yeah, it was already integrate the Chromium code. So in the future, we have from the integrated new version of the QUIC protocol in the Chromium. Is it right? The answer?
Oh, well, what I was asking is that...
Okay, I have some missing about your question.
So Google developers recently released a library called QUIC.
I see. But you mean that the Google often QUIC library and the branch of the Chromium part, but this is just to think of the main branch of the Chromium, and you say Google's QUIC library is also branch of the QUIC Chromium. So totally, this is the same protocol, and in the future, Stellite and Google's library will be same, but there is one difference. We have a friend client library and server, but also we are integrate the other server like Netty or Golang adapter or something like other language adapters. We have friend, so there was a big difference. Yeah.
Thank you.
Yeah, thank you. Okay. I think no question. I complete. Thank you for listening.